projects. In this video, we are going to explain about the project, which is remote sensing object detection based on convolution and Swin transformer. Remote sensing is the collection of the information about the Earth's surface and atmosphere using sensors on satellites or aircraft, offering insights for diverse applications such as environmental monitoring, agriculture, and disaster management. Remote sensing object detection is essential for interpreting aerial and satellite images with applications ranging from resource exploration and intelligent navigation to environmental monitoring and target tracking. Challenges in remote sensing object detection include small data scale, similar appearances of the objects, uneven distribution of targets, and complex backgrounds. Traditional object detection algorithms face limitations in handling remote sensing images due to their low feature extraction capability, especially for deep semantic information. These algorithms involve multiple steps such as feature extraction using methods like SIFT and HOG and the classification using SVM or random forest, resulting in inefficiency and suboptimal performance. The rapid development of deep learning, particularly convolutional neural network, has significantly impacted computer vision tasks. Deep learning based object detection algorithms fall into two categories. One stage, which is the first stage is YOLO and SST, and the two stage is RCNN and faster RCNN, each with its unique approach to generate object predictions. Inspired by the success of transformers in natural language processing, transformer based object detection algorithms have emerged, categorized into those using transformers as a backbone as the neck. To address challenges in remote sensing object detection, the project introduces the RAST YOLO algorithm, which is you only look once with region attention and Swin transformer as a novel solution. This algorithm combines the region attention mechanism with Swin transformer as the backbone to effectively extract features, thereby extending the information interaction with the range of feature map. Objective of the project. The objective is to elevate the accuracy of the object detection in remote sensing images, effectively addressing challenges associated with diverse target scales, complex backgrounds, and closely arranged small size targets. The goal is to introduce the region attention mechanism synerging with Swin transformer to extend the information interaction range of the feature map. This enhancement aims to bolster feature extraction capabilities for improved object detection. The project aims to leverage the C3D module to seamlessly integrate deep and shallow semantic information. This approach specifically targets the multi-scale challenge in remote sensing targets, optimizing the detection accuracy of smaller objects. The objective is to conduct extensive experiments and performance evaluations on DIOR and TGRS datasets. This assessment will provide insights into the effectiveness, efficiency, and robustness of the proposed RAST YOLO algorithm. The goal is to demonstrate RAST YOLO attains the state of the art detection accuracy when compared to baseline networks. A particular emphasis is placed on maintaining real time detection speed, ensuring a balance between effectiveness and efficiency in remote sensing object detection. We need hardware and software components to implement this project. Coming to hardware components, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. This step involves importing necessary Python libraries and packages that are required for image processing, machine learning, and web development. We have imported NumPy for numerical operations, OpenCV for image processing, TensorFlow for deep learning, and Flask for web development. The next step is exploring the dataset. Here we have substeps. Reading the image involves loading an image file into the program using OpenCV. Plotting the image using libraries like Matplotlib and OpenCV, which provides a visual representation of the dataset. The next step is image processing. Here we have substeps. Converting to a blob object is common in deep learning to prepare images for input into neural networks. Defining classes involves specifying the categories that the model will detect, and bounding boxes are the coordinates outlining the detected objects. Converting the array to a NumPy array facilitates efficient data manipulation. The next step is loading the pre-trained model. Here, reading the network layers involves loading a pre-trained model using a deep learning library. Extracting the output layers is crucial for obtaining predictions from the model. The next step is image processing. Here, appending the image and dealing with the annotation files are common steps in preparing dataset for training. Converting BGR to RGB, which is blue green red to red green blue, is necessary in certain cases as OpenCV often reads images in BGR format. Creating a mask and resizing the image, optimizing it for input into the neural network. The next step is data augmentation. Here, randomizing, rotating, and transforming the images are the techniques used to artificially increase the diversity of the training dataset, improving the model generalization. Here we install the packages that are required for the YOLO v5 and we process the data based on YOLO v5 model. The next step is building the model. This step involves constructing the deep learning model architecture, which is the common architectures for object detection including YOLO, which is you only look once. The next step is training the model. The model is trained on the pre-processed dataset, adjusting its weights using optimization algorithms. Flask framework with SQLite for sign up and sign in. Flask is used to set up a web application and SQLite is employed as a lightweight database for user authentication. Routes are defined for sign up and sign in. User gives input as the image. Here, user interact with the web application providing input in the form of an image. The next step is pre-processing the input. Here, the input, which is image, are pre-processed using the techniques developed earlier and the trained model is used for detection. Object segmentation and bounding boxes. The model's predictions are used to segment objects in the input and bounding boxes are drawn around the detected objects. Final outcome is displayed. The final result with the segmented objects and bounding boxes is displayed to the user through the web application. This provides a visual representation of the model's predictions on the given input. Algorithms which are used in this project are YOLO v5, which is the You Only Look Once version 5. It is a real-time object detection system that processes images in a single pass, predicting bounding boxes and class probabilities simultaneously. YOLO v5 is the fifth version known for its speed and accuracy in detecting objects in various scenarios. It is employed as the primary object detection model. Its real-time processing and high accuracy makes it suitable for detecting objects in remote sensing images with varying scales and complex backgrounds. The next algorithm is RAST YOLO, which is region attention and Swin transformer YOLO. It is an advanced variant of the YOLO object detection algorithm, incorporating the Swin transformer as its backbone and introducing the region attention mechanism. The Swin transformer enhances feature extraction by capturing both global and local information, allowing for effective multi-scale feature fusion. The RA mechanism specifically addresses the challenges posed by complex backgrounds in remote sensing images, improving the model's accuracy in detecting objects with varying scales. In the project, RAST YOLO is selected to enhance feature extraction capabilities and benchmarked against other algorithms for its effectiveness in remote sensing applications. The next algorithm is YOLO v3, which is You Only Look Once v3. It is an earlier version of the YOLO object detection algorithm. It divides the input image into a grid and predicts bounding boxes and class probabilities for each grid cell, offering a balance between speed and accuracy. It is used for benchmarking and comparing, showcasing the improvements achieved with the newer versions of YOLO v5 and RAST YOLO. The next algorithm is faster RCNN, which is region-based convolutional neural network. It is a two-stage object detection model. It uses region proposal network to generate potential bounding boxes proposals, followed by a classification network to predict the final bounding boxes and class labels. It is used for comparison with YOLO-based models as it represents a different approach to object detection with two-stage process. The next algorithm is RetinaNet. It is one-stage object detection model that addresses the problem of class imbalance in dense object detection. It introduces a focal loss function to focus training on hard to classify examples. It is included for comparison as its unique focal loss mechanism addresses the challenges related to imbalanced dataset and dense target distributions. As an extension, other YOLO versions are employed to enhance the performance. As also, extension we have built front-end using Flash framework for user testing with the user authentication. We have evaluated this project using different performance metrics which are precision, recall, and map. Here we have comparison graphs for the dataset which is DIOR dataset for all these metrics. This is precision comparison graph. Here on x-axis we have precision score for each algorithm, and on y-axis we have algorithm names. Precision is a metric that measures the accuracy of positive predictions made by a model. It is calculated as a ratio of true positive predictions to the sum of true positives and false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It measures the model's ability to capture all relevant instances of a class. It is calculated as a ratio of true positive predictions to the sum of true positives and false negatives. This is MAP, which is mean average precision. It is a metric commonly used in object detection tasks. It calculates the average precision for each class and then calculates the mean across all classes. Average precision, in turn, is the area under the precision recall curve. Here we have comparison graphs for the TGRS dataset. This is precision, this is recall, and here we have map. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the static folder. This folder consists files related to CSS, JavaScript, and Bootstrap file. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. Here we have app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. These are all the model files which contain the algorithm information and that will be loaded into the project code during runtime. This is the sign-up file. This file is the database file used to store the user information. This is the IPYNB file for the dataset which is DIOR. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to execute the file and code in individual cells, making it a popular choice for the data science. Now to execute the project, first we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. Here we need to type the command python space app.py and click on enter. This will compile app.py file and it will execute Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which is the localhost and the port, unless configured differently. This is the localhost and this is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on that and enter all the sign up details if we are signing up newly. I have already signed up and I have an account in it, so we'll directly log in. For that we need to click on login. Here we need to provide our credentials, which are the username and the password. So I'm giving my username and the password, and now we need to click on login. We have logged in successfully and we are redirected to prediction page. We executed the project for two datasets which are DIOR and TGRS. So first we will do the prediction for DIOR dataset. For that we need to click on this link. Here we can see a choose file button. First we need to click on that for uploading the images. So I'm clicking on choose file button. Here we have two dataset folders which are DIOR and TGRS. As we are doing prediction for the DIOR dataset, I'm opening this folder. I'm selecting the first image from DIOR dataset, click on open, and now click on upload. Here, from the image, two vehicles have been detected. Now we will upload the other image and see what will be detected. Click on back arrow. Click on choose file again. I'm selecting the second image. Click on open and now click on upload. Here we can see that three vehicles have been detected and they are labeled as vehicle. Click on back arrow. Now we will do the prediction using other dataset which is TGRS. For that we need to click on TGRS link. Click on choose file button. From the TGRS folder, I'm selecting the first image. Click on open and now click on upload. So here we can see that multiple objects are being detected by drawing a bounding box around the object with label and probability score. So here we can see that aeroplane has been detected with the pink bounding box and 0.85 probability, parking lot in green color bounding box and storage tank in blue color bounding box. Now we will upload the other image and see what will be detected. Click on back arrow. Click on choose file. I'm selecting this image. Click on open and now click on upload. Here we can see that four objects has been detected which are crossroad, ground tank, tennis court and parking lot. In this way, if we upload the images to the system, then the system will detect which object it is. Now click on sign out. Conclusion of the project. The project adopts a holistic approach integrating various state-of-the-art object detection algorithms including YOLO v5, RAST YOLO, YOLO v3, faster RCNN and Retina Net. This comprehensive strategy allows for a thorough comparison and evaluation of different methodologies. By incorporating a diverse set of algorithms, the project explores the strengths and weaknesses of each approach. The versatility aids in understanding the most suitable model for the unique challenges presented in the remote sensing object detection. The inclusion of YOLO v5, RAST YOLO, YOLO v3, faster RCNN, and Retina Net enables benchmarking against well established models. This comparative analysis provides valuable insights into the performance and adaptability of different algorithms. While the proposed RAST YOLO algorithm stands out for its innovative integration of the Swin transfer and region attention, the project broader scope contributes to the advancement of remote sensing solutions. The exploration of diverse algorithms enriches the understanding of their applicability and effectiveness. The project's findings lay out the groundwork for future research and improvements in the remote sensing object detection. The insights gained from comparing multiple algorithms can guide the development of more robust and efficient models tailored to the challenges of the aerial and satellite image interpretation.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.